In the previous video, we evaluated a slider crank mechanism using scale drawings. And in this video, we're going to analyse exactly the same slider crank mechanism, except this time we're going to be using trigonometric techniques. If you haven't already watched the previous video, it's worth going back and watching that first, because we're going to be making some comparisons between the values we obtain using trigonometric methods when compared to the scale drawing method. So in the top left-hand corner, we have our geometry. Now please note the geometry is not drawn to scale, and it doesn't need to be because we're going to be using trig in order to determine unknown parameters. We have a crank OA of length 80 millimeters, and that's rotating clockwise with an angular velocity of 85 radians per second. We have a second linkage, AB, which connects the crank to the slider, and that has a length of 250 millimeters. And the slider is constrained, meaning it can only move in the horizontal direction, and the slider itself has a mass of 3.5 kilograms. Now in the bottom right hand corner we have a list of the variables that we're going to be calculating. First of all, we're going to be calculating the velocity of B relative to O, which is basically the velocity of the slider relative to the origin. So as the crank rotates clockwise, our slider is going to be moving in this direction with velocity VBO. Then we're going to calculate the angular velocity of B relative to A. So we have the linkage AB, and the angular velocity of B relative to A is going to be in this direction, and we're going to calculate the magnitude of that. We're then going to calculate the angular acceleration of B relative to A. Now because the linkage AB doesn't have constant angular velocity, it's going to be experiencing an angular acceleration. Then finally we're going to calculate the inertial force for the slider, or the force required to move our slider B towards point O. Now all of the calculations we're going to be doing here are for when we have an internal angle of 55 degrees. If that angle changes, all of the variables would change. Okay, so hopefully you recall from the previous video, the first thing that we needed to determine was the unknown angles within our geometry. So we need to determine this angle here, and we need to determine this angle here. I'm going to call them lowercase a and b, corresponding with the points on the geometry. Now the way that we're going to determine angle lowercase b is using the sine rule. Now the general form of the sine rule states that a over sine a equals b over sine b. And this applies to any triangle. It doesn't need to be a right angle triangle. We do have earlier tutorials on the sine rule, if that's not something that you're familiar with, but we're going to be applying it here to our geometry. So let's rewrite that and make it specific to our geometry. We have an 80 millimeter linkage opposite angle B. Therefore, we can write 80 for the length of the linkage over sine B, and it's B that we're trying to find, equals 250, which is the second linkage, AB, and the angle opposite AB is 55 degrees. Now because I want to find the angle B, the first thing I'm going to do here is take the reciprocal of each side. So the top of each fraction becomes the bottom, and the bottom becomes the top. So that now the thing I'm trying to find is on the top of the fraction. The next thing I'm going to do is multiply each side by 80. So I'll get sine of the angle we're trying to find, B, equals 80 on top of the fraction, sine 55, and on the bottom of the fraction we have 250. Now the last thing I need to do to get B on its own is take sine to the minus 1 of each side. So the angle B that we're trying to find is sine to the minus 1 of 80 sine 55, all divided by 250. So running that through the calculator gives me an angle B equal to 15.20 degrees. Now, in order to find angle A, I know that the angles in a triangle add up to 180 degrees. So therefore, A plus B plus 55 must equal 180. Therefore, the unknown angle A is just 180 minus the 55 minus B, and we have a value for B of 15.20. Therefore, the unknown angle A equals 109.8 degrees. So I'm going to transfer those two angles to my geometry, and then we can start thinking about our linear velocity diagram. Okay, so as we're using trigonometry, there's no need for us to produce a scale drawing. However, we are going to produce a sketch so that we know which velocities we're trying to determine. Now, the first velocity that we're going to look at is the linear velocity of A relative to O, which we know is perpendicular to the linkage like so. Now, the direction for the velocity of A relative to O can be determined from our sketch, because if we have a horizontal datum here, then we can use the rule for alternate angles. We have an alternate angle here with the 55 degrees. Therefore, that angle is also 55 degrees. However, it isn't that angle that we want, it's this angle here. But what we can also see is that because we have a right angle between the linkage and the linear velocity VAO, this angle here must be 90 minus 55, or 35 degrees. Therefore, our velocity of A relative to O is at 35 degrees from the horizontal. We need to determine its magnitude as well, and we can use the straightforward conversion between linear and angular velocities that states that V equals R omega. We're trying to find V of A relative to O, and the radius of that motion is the length of the linkage OA. If you can imagine the linkage OA rotating, then A would draw a circle around O, and the radius of that circle would be the length of the linkage of 80 millimeters. So we have the length of the linkage OA, and the angular velocity was given in the question, and that was stated as 85 radians per second. Therefore, we have 80 millimeters expressed in meters, 0.08 times 85, which equals 6.8. And it's meters per second because it's a linear velocity. So for our sketch then, we need VAO at an angle of 35 degrees with a length of 6.8. Now, some of the other things we know that the motion of B relative to O, or the motion of the slider, is constrained horizontally. So if we label O and A, we know that B relative to O is horizontal. So it has to sit somewhere in this plane. And we can also determine the direction for the velocity of B relative to A. If we refer to our sketch in the top left-hand corner, we know that the velocity of B relative to A is perpendicular to the linkage. So here, in the corner, we have a right angle. So we have 15.2 degrees plus a right angle for that angle there. But the angle we're interested in is this angle here. Well, the simplest way to determine that angle is to do 180, because that's the sum of angles on a straight line, minus 90 for the right angle, minus 15.2 for the second angle. So running that through the calculator, we have 180 minus 15.2 minus 90, which is 74.8 degrees. So this angle here is 74.8 degrees. So we know that the velocity of B relative to A is at 74.8 degrees. Again, it's important to note that this isn't drawn to scale, but we have a velocity vector here taking us to point B, and we have a velocity vector here for B relative to O. So on our sketch, the original vector that we drew on was V of A relative to O. The horizontal line is the velocity of B relative to O, and the remaining line is the velocity of B relative to A. And we're going to calculate each of those unknown velocities using the sine rule. So first of all then, if we want to find a VBO, we need to determine the remaining angle. Well, we have the two other angles, so this remaining angle is just going to be 180 minus the other two angles. So 180 minus 35 minus 74.8. Now that gives us an angle equal to 70.2 degrees. Now we have all of the angles, we can find all of the unknown lengths. VBO over sine of the angle that's opposite, so sine 70.2, equals the velocity of AO, which we know has a value of 6.8, divided by sine of the angle opposite VAO, which we know is 74.8 degrees. Therefore, VBO equals 6.8 times sine 70.2 over sine 74.8. Giving us a value of VBO equal to 6.63 meters per second. Now, if we look in the bottom right-hand corner, the first variable that we wanted to calculate was actually VBO. So we've calculated that now, 6.63 meters per second. Let's add that to the list of variables in the bottom right-hand corner, and then we can look at how we can determine omega BA, or the angular velocity of B relative to A. Now, the approach that we're going to use to calculate omega BA is very similar. Before we can calculate omega BA, we need VBA. Well, VBA is opposite the 35-degree angle on our sketch. So we can use our sine rule. And again, we can either use VAO and the 74.8 degree angle, or we can use VBO and the 70.2 degree angle. I'm going to use 6.8 sine 74.8. Therefore, VBA equals 6.8 sine 35 over sine 74.8, giving me a value of VBA equal to 4.04. So now we've determined all of the parameters from our linear velocity diagram. We had the original velocity of A relative to O as 6.8 meters per second. We have the velocity of B relative to O on the right-hand side, the 6.63. And now we have the velocity of B relative to A of 4.04. But we don't want the linear velocity of B relative to A. We want the angular velocity. We can use the formula. V equals R omega. Therefore, omega is just V over R. And as it's omega BA that we're looking for, we need to use VBA as the velocity, 4.04, divided by the radius. Well, the radius of the motion for B relative to A is the length of the linkage AB. It's 250 millimetres. But we need to make sure we work in metres because we want our final answer in SI units. So we have 0.25 metres, giving us a value of omega BA equal to 16.17, and this is in radians per second because it's an angular velocity. Okay, once again I'm going to transfer that answer into the bottom right hand corner, and then I'm going to clear some space so that we can produce our acceleration diagram and find our remaining two parameters, the angular velocity of B relative to A and the force required to move the slider B relative to the origin. In the previous video, we discussed how a rotating linkage can experience two different types of acceleration. It can experience a tangential acceleration if the angular velocity is changing, and any rotating linkage is also going to experience a centripetal acceleration which acts towards the centre of rotation or the origin. If you'd like more information on that, then please watch the previous video to understand the reasons why a linkage can have two different types of acceleration. But assuming you've already watched that video, then we know that the linkage OA is going to have centripetal acceleration, and centripetal acceleration acts back towards the origin or back towards the centre of rotation. But it isn't going to have any tangential acceleration because its angular velocity is fixed at 85 radians per second. So we're only going to calculate the centripetal acceleration of A relative to O. And we also mentioned in the last video that we have two formulas we can use. We can either use V squared over R or R omega squared. I'm going to use R omega squared. The radius of rotation is the length of the linkage OA. And the angular velocity that we're using is the angular velocity of A relative to O, which was given in the original question. And that's omega AO squared. So the length of OA expressed in metres is 0.08 metres, and the original angular velocity was 85 radians per second, which is already in SI units. So we have 0.08 times 85 squared, which gives us an acceleration of A relative to O equal to 578, and our units for that are metres per second squared. Now we can do exactly the same for the centripetal acceleration of B relative to A. As B rotates around A, there's going to be an acceleration back towards the centre of rotation or back towards A. So we have A centripetal, B relative to A equals, and again we're going to use R omega squared. But this time the radius of motion is the length of the linkage AB. A is the centre, B is the outside of the circle, therefore the radius is the length of the linkage. In this case it's 0.25 metres, and the angular velocity is 16.17. The angular velocity we're using is the angular velocity of B relative to A that we previously determined. And we need to remember to square that. So the acceleration of B relative to A equals 65.29 metres per second squared. Now, because the angular velocity of B relative to A isn't constant, it's going to change as the crank rotates, we're also going to have a tangential acceleration of B relative to A. So we're going to have a tangential acceleration of B relative to A, but we don't yet know the magnitude of that. And we're also going to have an acceleration of our slider B relative to the origin. And again, we don't yet know the magnitude of that. However, what we do know is we know the direction of the centripetal acceleration of A relative to O, because we know it acts towards the centre or towards the origin from A. We also know the magnitude of the centripetal acceleration of B relative to A, and we also know its direction because it acts in the same direction as the linkage from B to A, back towards the centre. We have a tangential acceleration of B relative to A, and we don't yet know its magnitude, but what we do know is its direction. Because it's tangential to the centripetal acceleration, it must be in the same direction as the previously drawn velocity vector for B relative to A. And finally, we don't yet know the magnitude of the acceleration of B relative to O, but again we know its direction. It's constrained and it can only move horizontally, so its direction must be horizontal. So what we're going to do is piece together all of these bits of information, and by doing so we can produce a sketch of the acceleration diagram. Now where I'm going to start with this is by sketching the centripetal acceleration of A relative to O, because I know it has a magnitude of 578 at an angle of 55 degrees. And we know it acts towards the centre. Next, I'm going to sketch on my centripetal acceleration of B relative to A. Now we know its direction is 15.2 degrees. We calculated that earlier as 15.20, and we know its magnitude is 65.29. For the remaining two acceleration vectors, we know their direction, but we don't know their magnitude. We know the direction for the tangential acceleration of B relative to A is at right angles to the centripetal acceleration of B relative to A. So we have a right angle in there. And for the slider, we know that its acceleration is horizontal. So we know it's in that direction. So we can complete our sketch of our acceleration diagram like so. So we're going to need to find our remaining two accelerations. One of the accelerations we need to find is the acceleration of B relative to O, and the other acceleration we need to find is the tangential acceleration of B relative to A. So let's consider how we're going to do this using trigonometry. And the key to this is by adding some additional triangles onto this diagram. We have a triangle here, let's call that triangle 1 for reference. We have a triangle here, let's call this triangle 2, and we have a triangle here, let's call that triangle 3. The other pieces of information that we're going to need in order to determine these unknown accelerations is the total height of the rectangle that we've just sketched and the total width of that rectangle. So we're going to need to work our way round finding unknown lengths until we can find the acceleration of B relative to O, represented by the blue line along the top, and the tangential acceleration of B relative to A, represented by the final unknown vector. Okay, let's clear some space and look at each of these triangles 1, 2 and 3. So first of all, using triangle 1, we can find the total height of our rectangle, and we can also find the partial distance between here and here. Let's call this lowercase w1. We know the hypotenuse of triangle 1 is 578, and we know the angle is 55 degrees. Therefore, the height is the opposite of that triangle, and w1 is the adjacent. From trigonometry, we know the opposite is hypotenuse sine theta. Therefore, in this case, the opposite is 578 sine 55, which equals 473.47. I won't attach any units at this point, but the units would actually be meters per second squared if we were to add units to that. We know from trigonometry that adjacent is hypotenuse cos theta. So in this case, 578 cos 55, which equals 331.53. So therefore, the value of h is 473.47. And the value of W1 down here is 331.53. And we've established that using triangle 1. So next let's look at triangle 2, and once again we know the hypotenuse. The hypotenuse there is 65.29, and we can actually use that triangle to calculate this second partial distance for the width. Let's call it W2 for consistency. And we can also use it to determine this partial height here, which we'll call H1. So for triangle 2, we can see that H1 is opposite the angle. So we can write H1, the thing we're trying to find, is the hypotenuse of 65.29, sine of the angle of 15.2, giving us a length equal to 17.12. And we can also find W2, so it'll be 65.29 cos of the angle of 15.2, which is 63.01. So we have over here 63.01 for W2 and 17.12 for H1. Now to determine H2, this distance here, we don't need to do any trigonometry because we know the total height H and we know the height H1. Therefore H2 is just going to be the total height of 473.47 minus H1 of 17.12. And that gives us a value of H2 equal to 456.35. So up here, 456.35. Now, although our diagram's becoming a little bit crowded, we can also determine this angle in here in triangle 3, because the angle inside triangle 3 is going to be 15.2 degrees. I'll just explain how we know this in the bottom left hand corner. We have triangle 2 with an angle of 15.2 degrees and a right angle, meaning its remaining angle is 180 minus 90 minus 15.2, or 74.8. We then have a right angle along that straight line, and then we have the angle that we're trying to determine on triangle 3. Well, once again, we have three angles on a straight line. We have 74.8, we have 90, and the angle that we're trying to find. So 180 minus 90 minus the 74.8 brings us back to 15.2. We're going to use that angle and the length H2 in order to determine our two remaining lengths. We're going to determine this length here, which I'm going to call W3. And we're also going to determine the thing we set out to find originally, the tangential acceleration of B relative to A. I'm just going to clear some space for these final calculations. So using triangle 3, and we want to find W3, we can see that W3 is opposite the angle, and we know the length of H2, which is the adjacent on the triangle. The trigonometric formula we're going to need to use here is tan theta is opposite over adjacent. or opposite is adjacent tan theta. If we want to find the opposite, we need to do the adjacent, which we know is 456.35, times tan of the angle, which we know is 15.2 degrees, giving us a value of W3 equal to 123.99. Now, the other thing that we said we could find was the tangential acceleration of B relative to A. And that's represented by the hypotenuse on our triangle. So we can either use sine or cos here. Let's use sine. We know sine theta equals opposite over hypotenuse. Therefore, hypotenuse equals opposite over sine theta. Well, opposite is W3. And sine theta is sine of the 15.2. Therefore, the tangential acceleration of B relative to A is W3, which we just calculated, 123.99, over sine 15.2, which gives us a tangential acceleration of B relative to A equal to 472.90. And that's going to be in meters per second squared, because it's a linear acceleration. But we don't want the linear acceleration of B relative to A, we want the angular acceleration. And there's a relatively straightforward formula to convert between linear and angular acceleration. A equals R alpha. But we're trying to find alpha, the angular acceleration, which is just A over R. So the linear acceleration that we need to use to determine an angular acceleration is always going to be the tangential linear acceleration. The reason being is because the angular velocity is tangential to the link, therefore the angular acceleration that we're interested in must also be tangential to the link. So we're going to use AT for B relative to A, and we're going to use the length of the linkage AB. Therefore, the angular acceleration of B relative to A equals the tangential linear acceleration of B relative to A, 472.90, divided by the length of the linkage in meters, 0.25, giving a value equal to 1892 radians per second squared, accurate to the nearest whole number. Let's add that on the right hand side, and then we just have one final calculation to do. So 1892 radians per second squared. Okay, so the final thing we're trying to calculate is the force required to accelerate the slider, or the force required to move B relative to the origin. Now the formula for force is just mass times acceleration. So we already have the mass of the slider. The acceleration that we don't yet have is the acceleration of B relative to O. Now we can get this from our diagram, and it's actually easier than it may seem because we can determine our overall width W. And if we look at our acceleration diagram, we can see that acceleration of B relative to O is just the overall width, capital W, minus W3, which we previously calculated. So we can write the acceleration of B relative to O equals capital W minus W3. Well, capital W is just W1 plus W2. So we have W1 plus W2, which gives us the total width, then minus W3. Therefore, the acceleration of B relative to O equals 331.53 plus 63.01 minus 123.99, which was our value for W3. Therefore, the acceleration of B relative to O equals 270.55 meters per second squared. Therefore, our force of B relative to O is our mass of 3.5 kilograms times our acceleration of 270.55, giving us a force equal to 947 newtons, accurate to the nearest whole number. So adding that in our bottom right hand corner completes our calculations. Now, I appreciate that there's a lot of steps involved there, but we do have alternatives. We can use the scale drawing method in order to determine our unknown velocities and unknown accelerations, or we can use the trigonometric method. And although both methods are quite complex, they actually only really rely on a couple of basic principles. The first principle that they rely on you understanding is that linear velocities of rotating components act tangential to the linkages. And another important aspect is that there can be two accelerations. There can be a centripetal acceleration acting towards the centre for rotation, and there can also be a tangential acceleration, but there's only a tangential acceleration if the angular velocity is changing. So I hope you found this video useful, and thanks for listening.